Hello, good evening, both of you. Hello, Ankita. Hello, Mukul.
Yes, ma'am.
Hi, where are you from?
West Bengal.
Okay, so you have started the course. You have watched the lectures.
Yes,
Okay, so and what stage of education you are in right now?
BSc first year.
Okay, great, great. And Ankita, you? Okay, so I am Shruti, and I will be taking the live sessions for this course. And I'm from IIT Bombay itself. I'm a PhD student, second year. And so this is the first session. There will be 12 sessions for this course as it is a 12-week course. And I hope you have watched first few lectures. Isn't it, Mukul?
Yes, ma'am.
Okay. So how are you liking the lectures? Understanding or not understanding at all?
Yes, I think this is the first week, so I think I've learned this.
Okay. And did you submit the assignments?
Some questions I've submitted, and after the live session, I will submit the most.
Okay, okay. And are you planning to give exam for the course? Because there will be an exam in the month of October, I guess.
Yes.
Okay, so have you registered for it already, or you will register?
No, I think it's MSc level course. I think Symmetry and Group Theory.
Yes, it is an
So,
MSc course. Yeah.
so I'm seeing this, and after seeing the level, I will decide it.
Okay, 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 great. So it's good you are like getting into the course beforehand. So I guess for BSc first year it will be little too much, but it won't be that much because sir has explained in great detail in the lectures, and I'll be solving the assignment questions, but I'll be solving the assignment, only those assignment for which the deadlines have passed, because I cannot give answers to the assignments whose deadlines are coming up. Okay.
Okay.
So let me introduce a bit
Demo question,
about
if any.
demo questions. Yeah, I will provide you some questions. So let's.
Has it any relation with the mathematical group theory?
Yes, it has.
I
So
have studied this, so I think there will be helpful.
you have studied the group theory in maths.
Yes, ma'am. Yes.
Okay. Yeah. We won't be dealing much with the mathematics, but you should be able to understand matrix algebra.
Okay.
Yeah.
Hello,
Hi. Hello.
hello. Pardon me for this.
Hi, Ankita. How are you?
Hello. I'm fine. I'm fine.
Yeah.
Actually, there was a net issue, and I'm unable to connect with you.
Okay, that's fine. That's fine. So, where are
Okay.
you
Okay.
from?
I'm from Kerala.
Okay, and what are you studying now?
I have completed my MSc.
Okay.
Now I have been taken admission for BA.
Okay, B.Ed. Yeah, very good.
Yeah.
Okay.
Yeah. Thank you.
So you must be aware of this group theory lectures, group theory subject, right?
Yeah. Yeah. Sure. Sure. I have been studying in my MSc classes,
Yeah, yeah.
and I am very interested in this topic too.
Okay, great. So there is
Thank.
like we have Mukul with us, and he's a first year student. So I'll be
Ah,
trying to explain each and every detail because I don't know, like the students here are like from different backgrounds. So
okay.
it may be a little boring for you, but please
Ah,
bear with me, okay?
it's okay. It's okay. It's okay. It's not a problem.
Yeah. So the course is all about symmetry, and symmetry plays a very important role in the analysis of structures of molecule, and then we, depending upon the symmetry, we get to know how the molecules bind with each other, how atoms bind with each other and form molecules, and what is the symmetry of the molecule, and depending upon the symmetry the molecules show certain properties. So this whole thing is the game of symmetry. So first, today I'll be discussing like basic symmetry operations. So first thing is I'll be discussing is the symmetry elements and the operations related with it, and depending upon them we classify molecules into different point groups. So this is called the symmetry classification. Okay, so we have a question that how do we decide so how do we decide that which molecule belongs to which symmetry group? So there should be some criteria to decide this. So this criteria is called the symmetry elements. So every molecule will have certain symmetry elements associated with it, and depending upon what and how many number of symmetry elements the molecule has, we classify them into various different categories. Now let us come to the what these symmetry elements are. So Mukul, you have any idea about the symmetry elements?
Yes, ma'am.
Okay, what are these?
Cn, sigma I,
Okay, and there is one more.
Sn.
Yes, very good. So we have first one is sigma or symmetry plane, or let's start with proper axis of rotation. So this is called Cn. Now what happens in Cn is we have to, after applying the operation Cn is a axis. Cn means an axis, and here n means that after rotating the molecule by 360 by n degrees we should get the molecule back. Identical configuration of the molecule back. Okay, so suppose So starting with the simplest one, suppose we have water. So, and in this course it is very important that we draw the molecules with their proper shape or the hybridization. If I draw water like this linear, then we will be deciding the point group based on different symmetry operations which it doesn't has in actual. So we have to draw the molecules considering their 3D shape, how they are actually present. Okay, so this will be wrong, this will give us wrong information about the point group. So we have a water molecule like this with two lone pairs. So if I want to draw an axis, suppose I'll draw an axis like this. Okay, this axis divides the passes through the oxygen atom. Okay, so in 3D it will okay, I can show you the 3D one. So let me share one more screen. Okay, so my screen is visible, right? Sorry, I'm using two devices, so I got kicked out when I switched to one. Okay, now this is a, I'll suggest you guys to go through this website. It's called Symmetry @Autorbn, and it has the point group classification of most of the lot of molecules actually. So let's see. We are discussing CN. Let's see this molecule. Okay, this is ammonia. Okay, in which this one, the blue one, is nitrogen and all other three are hydrogen. So it has a pyramidal structure. Okay, now we have to think of excesses passing through this molecule such that when we rotate the molecule by 360 by n, so we can have multiple orders of the axis, C1, C2, C3, C4, C5, like that. So C1 means 360 by 1, that is 360, so a complete 360 rotation will work. And then C2 is 360 by 2, that is 180. So after rotating the molecule around that axis by 180 degrees, you should be able to get that molecule back like the same configuration. Okay, so this molecule has C3. I'll show you. So this is the C3 axis. This is how it looks. This is the C3 axis. When I'll rotate the molecule, now C3 means 180 by 3, 360 by 3, so 120 degree rotation. So after 120 degree rotation, this is how the molecule will look like. Now H remains H and N remains N, so there is no abrupt change in the molecule before and after rotations. Okay, So this is called a proper axis of rotation. The molecule is said to have this C3 axis of rotation. Now suppose if I apply C4, how can I change the shared screen? Okay, I'll have to stop this. Okay, I'll present from here itself. Okay, now as I was saying, now consider this hydrogen atom, this water molecule, and we have hydrogen atom A and B. Let's name it. It doesn't mean that these two atoms are different. This is simply for our visual interpretation that I have named this both hydrogen atoms by A and B. Now let us try with C1. C1 means 360 by 1, that is 360-degree rotation. If I'll rotate it by 360 along this axis, this dotted line, so this is the rotation. So what will happen? It will be like O, HA, HB, and the axis will remain here. Now C2 means 360 by 2, which is 180-degree rotation. So the changes will be, now after applying 180-degree rotation, the hydrogen atoms will change their place. Okay, so this will move here and this will move here. Okay, so here it will be B, it will be A. But since the hydrogen atoms are identical, we cannot distinguish between one hydrogen atom and the other. We say that this molecule contains C2. It also contains C1, which is basically another symmetry element. It's called identity element. It is denoted by E. Like the axis of rotation is denoted by Cn. N can vary 1, 2, 3, 4, and likewise. Identity element is denoted by E. Now let us try for C3. So if we check C3, which is 360 by 3, 120-degree rotation. So what will happen? Now suppose this is a triangle C3. Now after C3, this will be HB, this will be HA, isn't it? Now the configuration of the molecule has changed, right? And we had two lone pairs over here. Since the configuration has changed, configuration means how it looks in configuration has changed, so it doesn't contain C3. Okay, the configuration means the arrangement of atoms in space should not change. Now here HB has changed its location, HA has changed. O remains same, but A atom HA and HB has changed their places. So it doesn't contain a C3 axis. Okay, so that's how we decide which molecule contains which symmetry axis, rotational axis. Okay, so I showed you example of ammonia, right? Okay, now this had C3 passing through the nitrogen atom and the lone pair of atoms. C1 is definitely there. C1 is basically E. So a rotation by 360. So if you rotate anything by 360 degree, it will retain its original configuration. So every molecule or everything has an identity element. So let us write this. Our second uh, symmetry operation is called identity, which is denoted by E. So you can ask that why do we have identity when all the molecules have this operation? So how does it help to classify them? Since everyone has this, so what's the need of defining this as a symmetry operation? Can anyone answer this?
Because we count that in the final order,
What
in for the order of the molecule or the
order?
symmetry.
Okay, but if we don't have this, order will get reduced.
Yeah, that's why we need the identity
No,
element
no,
because that.
we can we can reduce the orders of all the molecules by one. What's the need of having E?
uh,
So E basically does nothing to the molecule, no change. Or actually it is rotation by 360 degree. And also this is a point. Okay, so this is our second symmetry element. Now moving on, we have one more which is called sorry I already discussed the axis, so this is called the rotation plane or symmetry plane. Okay, so plane means it's a, we had in axis we had a line as a symmetry element. Now we will have a plane. Okay, plane in different directions. So suppose this is x, y and z. So this plane will be, and the plane is denoted by this symbol sigma. This will be sigma x and y, sigma xy. Okay, so if I draw a plane like this will be sigma yz. Okay, and I draw this plane, this will be sigma xz. Okay, so depending upon which direction it is oriented, we will have these two alphabets as subscript. Now sigma, considering this example itself, now does this molecule has a plane? Now what a plane does, sigma plane, its plane reflects. Okay, it's like mirror, so the operation is reflection through the plane. Okay, like when we see mirror, what do we see? We see our reflection, right? So similarly, the sigma symmetry operation reflects the molecule in a particular direction. Suppose we have sigma x y, so the reflection, you will put the plane in the xy direction and the reflection will happen in the z direction. Okay, suppose okay, now if I draw a plane, so this is my plane, can I put this plane in this molecule so that the configuration of the molecule doesn't change? Can I put xy?
No.
Okay,
If N and HA are on the XY plane, then the configuration will remain the same.
yes, so we can put the plane like this. Okay, or let me draw it better. This is my HA, this is the bond coming towards me, HB, and this is the bond which is like going inwards, and we have this lone pair. Okay, if I draw a plane which contains this, okay, so this is my plane. Okay, the plane contains the lone pair, the nitrogen atom, the NH bond and the HA atom. Then what it will do, it will reflect. And the things on the plane will remain on the plane. So after reflection, HC will come up, okay, towards you or towards me, and then HB will go on the back side. So what a plane does, it's like rotation by 180 degree. So this got here and this got reflected here, and nothing happened to these atoms on the plane. So likewise you can place the planes on each of, suppose we have kept this plane in on NHA bond. Now you can keep the plane NHB bond, okay, and you can have another plane on NHC bond. So it will have 3 sigma planes, okay. So this molecule had one C3 axis and 3 sigma V. Now I'll tell you why it is called V later. And it had identity because all the molecules will have identity. So this ammonia molecule has these 3 symmetry elements associated. Now let's come to the next symmetry element. Okay, we were discussing one more example, which was water. So let's finish this as well. So this has a plane here. Okay, can you imagine the plane going through the oxygen atom like this? So the plane is in this direction, okay, and here we have oxygen, on the other side one edge, on this side one edge, okay. So this will HB. Now this will reflect the molecule like this. So it also has a sigma plane. And there is one more plane which is like this. Okay, if I keep all the atoms on this plane, so it's like the plane passing through the, we suppose that H atoms and the O atom is spherically symmetric. Okay, then the plane will be such that it cuts the atom in half, okay. So this is the molecule. The plane will be such that it cuts the atom in half like this. So this is one more plane, and since this plane contains all the atoms in the molecule, this plane is called molecular plane. Okay, so we discussed the hydrogen atom and the water molecule and the ammonia molecule, which contain the symmetry plane. Now there is one more operation. So we discussed 3. One was axis, second was identity, third was plane, reflection, and there is fourth, which is called improper axis of rotation. The proper axis of rotation was Cn, okay. Now Sn is improper axis of rotation. Now Sn means it's a combined operation. So Cn plus perpendicular sigma, okay. So which Cn means what? Rotation by 360 by n degrees, and after this rotation you have to do a mirror plane reflection. You have to do reflection of the molecule, and not any reflection, reflection through the plane perpendicular to Cn. Okay, now let me show you this. So if I have suppose this is my rotation axis, okay, I'll draw. Now this is my rotation axis, that is CZ, because rotation is along the Z axis. So what will be the perpendicular plane?
XY plane.
So XY, yeah, this plane will be the perpendicular plane, sigma XY. And you can see by the this subscripts, those are complementary. CZ will be followed by sigma XY. If you will have a rotation along this CX, then you have to follow a plane which is like that, sigma YZ. Okay, so this is what is meant by perpendicular, a rotation followed by perpendicular reflection. That's why it's called improper axis of symmetry. Okay, and it's also interconvertible. Suppose you do what is left, this plane is left, sigma XZ. This also you can follow by rotation along Y. Okay, so it does not matter whether you perform the rotation first and reflection later or vice versa, you will get the same answer. Okay, so CZ, now the operations are written as dot product will be equal to, okay, so the order in which you perform the operation does not affect your result. If the molecule has Sn when you perform CZ first and sigma XY after that, it will still have Sn if you perform sigma Y XY and then you perform CZ. Okay, now we are left with the last. So we discussed axis, we discussed identity, then we had what, reflection, then we had improper axis, S, sigma E, axis is C. Okay, and the last one, the fifth one, is called inversion center, and this is denoted by I. Now inversion center means what? The word inversion means what? It should invert the molecule. Okay, so inversion means, suppose, let's start with the maths one. Suppose you have a 2D plane. Okay, now this is a point, this is a position vector, and at x it is 3 and at y it is 4. Okay, so this coordinates of this point will be 3, 4. Okay, When you will invert it, where this position vector will go?
-3, -4.
Yes, so it will come in the third quadrant, right? Here. So the coordinates will become -3, -4. Third quadrant, both will be negative. Similarly, when you invert a molecule, all the coordinates of that molecule should negate itself. Like if the molecule has, the atoms of the molecule has coordinates x, y and z because a molecule will be 3D. So after applying the inversion symmetry, the coordinates of all the atoms should become like this. It should negate itself. Okay. Let's say and there's another way of explaining this. Suppose this is a something x and here I have x. Okay, this is an example from the assignments itself. So when you see that the molecule is symmetric such that if you extrapolate this in this direction, you get the same atom, and if you extrapolate x in this direction, you get the same atom. Okay, and here is your inversion center. So the inversion center, it's not necessary that the inversion center should lie on an atom. It can lie on an atom, on a bond, or on anywhere in space. Okay, now in this example here, the inversion center lies somewhere in the space because the molecule is like this. These are all C bonds and this is some halogen atom. The inversion center is in between these bonds, in between the molecule. So when I flip this molecule around this center, I will get the same molecule back. Okay, let's name it as A and B. Now this molecule when flipped, so this is gonna come over here and this is gonna go over there. So this will be XB and here we will have XA. You have to imagine this in 3 dimension. So you are flipping the molecule around this point. Okay, if you will flip around anywhere, around any other point, suppose if I flip around this point, I will get something like this. So the orientation and the configuration has changed in this case. So inversion center is not here, the center is here itself. Okay, so this is the concept of inversion center, that the coordinates gets negated and the atoms when you flip the molecule or when you extrapolate on both the sides from the inversion center, you get the same atom. So what I meant by my last statement is, this was my inversion center and this was my halogen atom A and this is my halogen atom B. So when I go in top up direction, okay, this is my Z, this is my X and this is Y. So when I'm going up and like here around this direction, okay, I get this halogen atom XA. When I go on the opposite side here, I get the same atom. Imagine this in 3D. It's like a twisted table, a table which doesn't has these two legs. One leg, this leg is in the ground, and the other leg has been twisted up. It's like this. So when you will see it from this point, if you will look up, you will find this leg. If you will look down in the same angle, you will find this leg which is touching the ground. So this is the meaning that on extrapolating on both the sides at the same angle, you should get the same atom. Okay, so here we have the same atom, halogen atom. So the molecule is said to contain an inversion symmetry. I can show you the inversion symmetry from here. One second. Okay, now look at this molecule. Now what symmetry elements does it contain? Now forget about what atoms are these. Suppose I'll show you here. Now we have A, and all other atoms were same. So okay, let's be some realistic, and this is M. Suppose it is some metal, and all other are halogen. Okay, so it's a molecule like this, a planar molecule. Now what symmetry elements does it have?
C4.
Yes, but before that,
It will
I.
have C2.
C2, C1, C2, that is identity, C2, C4. Does it has C3?
No.
No, okay. And what else?
Molecular
Sigma.
plane.
Sigma planes. How many planes are there?
Molecular plane and perpendicular to the axis.
Yes. I wish I could show here. Oh, it's just showing. Tetrachloroplatinate. Okay, so the planes will be, you can't see my cursor. Okay, the planes will be, there will be plane
Dihedral plane also.
like this, which is dihedral plane. There will be planes like this, isn't it?
Yes.
Okay, now inversion center is there.
Yes.
Yes.
So the inversion center is at the central atom in this case, isn't it? So inversion
Yes.
Yes.
center is here at the center. This dark green thing is the inversion center. So in this case, the inversion center lies on an atom itself, not somewhere on the space. Okay, and in some case, okay, in this case this is a benzene molecule. Here the inversion center lies in between. Can you see this green dot? So when you will move from that green dot to any two directions which are opposite to each other, you will find the same atom. Suppose now the benzene, we will have H atoms on all sides, right? On all carbon, one H. Inversion center is here. So if I move this side, I get CH bond. If I move this side, I get CH bond. It's true for on all other sides. Okay? So in this case, especially it is true for all other sides. In whatever sides you get the identical atom or identical bond. But if I have the same example which I told first, X, X, and here I have Y, here I have Z. So does it have inversion center now?
No.
No.
No, the inversion center is gone because of, maybe because of
Why is
these
that?
two, YZ. Had it been YY, now we have the inversion center, right? Because when you will flip around this little dot here at the center, you will get this back, this configuration of the molecule back. So because of any pair going wrong, you will lose the symmetry element. Okay, now let me show you more symmetry elements from this. Now we talked about identity. Now can you see this molecule? It's like a staggered methane in which all four atoms are different. So it's like CHFClBr. It's mentioned on the right side. So all four atoms are different. Bond lengths are different, the atoms itself are different. Okay, does it have any axis of rotation?
It does not have any symmetry element as it's chiral.
But it has one symmetry element.
E.
Yes, every molecule will have E, definitely. You never say that it doesn't has any symmetry element. E is a symmetry element. Okay, next is this similar kind of molecule. So you see this molecule, central atom is sulfur, double bonded to oxygen and single bonded to chlorine and bromine. So this molecule also has E only. Okay, now let's move to proper rotations. Yes, now this is what I was talking about in the first place, the water molecule with C2. Okay, so when you will rotate around this axis, the atoms will interchange their places, but the configuration of the molecule will remain same. Okay, this is proper. proper axis. Now similarly this is what? Ethane. Now which form of ethane is this?
Staggered,
What is the other one?
eclipsed,
Can you find out what are the symmetry elements in the eclipsed form?
sigma, C3, and C2.
Now let's check here first in the staggered form. Everyone understand why is it staggered? Because we have two inverted y's. So on the front first carbon atom towards your side you have a erect y, okay, and on the back side the y is inverted, right? Now if I'll flip it, it becomes like this. The inverted y comes towards you and the erect y goes behind. So this is staggered form. Eclipse form will be each bond facing the other one on the back carbon. Now let's see the rotations. First, and the thing which I told that say identity element can pass through anywhere like the atom or bond, or it can be in space. Same is true with all other symmetry elements. It is not necessary that it should pass through an atom or a bond. It can pass through anywhere in space or through a bond or through atoms or a, yeah, like that. So in this case this C2 is passing through a bond. There is no atom involved in here. Okay, so you see what happened. Let me keep it like this. So the two atoms on this side, so the molecule looks like this now. Okay, since all the atoms are H, so I am keeping it with the same alphabet. Now the C2 which is here, C2, what it will do will the skeleton should remain same. If the skeleton changes, then it's not a symmetry operation. So these 2A will go in place of this and this. So we have A. Let me write 1, 2, 3 and 1, 2, 3. So according to the numbers, they will change their place. Now A2 will take place of red A2 and A3, green A3 will go in place of red A3. So we will have here A3, here A2 and A1 will come here. So here it will be A1 and likewise the others will be A1 here, A2 here, A3 here. Okay, so this is happening as you can see here. See again. Okay, can you visualize this?
Yes.
Okay, so like with this is one C2, there are other C2s. One is this. So what this does, now this C2 is like this. If you want to see the difference between the two, you see these two are at an angle, and there is one more. So if you see these C2s are passing in between these two bonds, like dihedral bonds, not proper exact bond, but this plane, this solid angle. Okay, so we have these three C2s. Now what this C2 does is, okay, this will also have similar operation but in a different direction because its orientation is different. And the other C2, okay, this is 1, this is 2, this is 3. All three are different. If you want to check, you can go to this website on your own and you can check better. Now this was C2. Now come to C3. Now C3 passes through this. Can you see it's a 2 triangle inverted? So if you pass it through one triangle, it comes out from the other side, and then because it's triangular and C3 is 120-degree rotation, it fits in perfectly like this. So in C3, atoms attached to the same carbon atom, the hydrogen atoms which are attached to the same carbon atom is changing place among themselves. What I mean is, so I have C1, I have C2, and let's name it H1, H3 dash, H1 dash, H2 dash. Now in C3, these are changing place among themselves. Okay, but in C2, because C2 was passing through here in between the bond, it was interchanging the hydrogen atoms like this. It was not actually interchanging. Like visually when you see, you can think of the hydrogen atoms are getting interchanged from here to here, but actually the carbon itself, the C1 and C2 are also rotating. But when you see this animation, now you see this, the whole thing is rotating. Like this whole part and this whole part rotates on its own. This comes here, this goes there. But when you apply C3, there is a rotation among this group itself. Okay, okay, so we discussed some symmetry elements. And let's see what I have next. Okay, let's come to week 0 assignments. So did you guys submit this assignment?
Yes.
Okay, we
Yes.
got everything correct?
No.
Oh, no, but then after you submit it, I think you can see the answer. So,
Okay, yeah, week 0 is still, you can submit, it's still live.
It does not get added to the main marks.
Okay, okay, yeah, it doesn't get added. This is just for your practice. Okay, so, okay, tell me the answers for the first question then. The following molecule given above, the symmetry elements that are not present over here. So first one is point of inversion. Does it has point of inversion?
no.
It,
Mukul?
it should have on the bond X bond.
But if it will have on the XX bond,
It does not have any criteria that it should be on the center of the molecule.
yes, here. You mean it should be here, right?
Yes.
Okay. But now check on this side. Here what we have, hydrogen atoms. See, it's a C, like cyclobutane kind of molecule. So we have
Oh, sorry.
like this hydrogen atoms on this side. So when I go to this side, here I find an H atom. But when I extrapolate on the opposite side, here I don't have anything. Right?
Okay, sorry.
Yeah. So we don't have inversion center here. The inversion center should be able to invert all the elements in the molecule, all the atoms in the molecule. Okay, so it doesn't have. And for an inversion center to be here, this bond should be reflected here. We should have an X atom here, but it's not there in this molecule. Okay, so there is
Okay.
no inversion center. Okay, the second one, the second option, C2 axis of symmetry.
Yes, it has.
Which one?
Along the X connecting bond,
Which C2 is there?
which C2 means
Which direction?
left to right.
Okay, so you okay. Now tell which C2.
X-axis.
Yes, so it has like this. Is it fine?
Okay.
So this is out of plane rotation, out of plane, because the molecular plane is what?
XY plane.
So this is the molecular plane, right? Here is your cyclobutane kept. This is the molecular plane, and C2X, what it will do, it will rotate now. C2X will rotate this here and this will go here, so it is out of plane rotation. The front side, suppose this top side was my green colored, okay, and the bottom side of the molecule was something like this red colored, okay. When you apply this, what will happen, the bottom part, the bottom side will come up, and the top side, which was the green side earlier, it will go down. And here you had XA, XB. Now XA will come here and XB will go here. Is this fine?
Yes.
Yes.
Okay. So it has C2. What about C2 along the other directions?
No, it doesn't have C2 in any other directions.
Yeah, so if I keep a C2 along the Z direction, so this is C2Z. So how will it rotate the molecule? The result should be
XA and XB on the left side.
yes. So XA will be here and XB will be here. No, sorry. Like this. XP will go that side. 180-degree rotation. So now here you see the configuration of the molecule has changed. So it doesn't have C2Z. C2Z is not present. Okay, and can you draw what will happen if we apply C2Y? So C2Y will be like this. Where will the XA and XB will go? Let me name. 1, 2, 3, 4. Now how it should change?
1, 2, 4, 2 to 3.
1 here, 2 here, 3 here, 4 here, right?
Yes.
And likewise the atoms will change their direction. So at 1 XA was up, so here XA will go down, and XB was down, it will come up. So it doesn't has C2Y. So it has one C2 along the X direction. So the question asked the following elements that are not present. So inversion center is not present, but C2 is present, even though only one C2 is present, but C2 is there. So this is correct. Now C4 axis.
Not present.
Yeah, C4, suppose any C4. Now C4 also you can apply on all the directions, but the easiest one, let's say C4 along the Z direction. So how will it change? One, two, three, four. Now tell me. By the way, this is a perfect square, not a rectangle. Now tell me where 1, 2, 3, 4 will go. C4 means
1 to 4, 2 to 1.
90-degree rotation. Degree rotation anti-clockwise. So in place of 1, what shall I write here?
2.
2. Then here
3.
3. So here will be 4. Here will be
and
1.
1.
And what about the orientation of XA?
It should remain same.
Yes. So XA will be here itself. And XB will be here. So in last example we saw it changed its direction when the axis was along Y, but along Z there was no change in the orientation. XA was up and after the operation it was up. So since the bonds are along the Z axis, any change along that axis will not change the orientation of the bond. But if you will do a perpendicular operation, a reflection or rotation, you will change the orientation from up to down and down to up. Okay?
Okay.
Now if I do along this C4x, now tell me, after the operation what should be the orientations?
It will be same, just the direction will change.
Yes. So where shall I write?
The molecule will be in the perpendicular plane to the previous one.
So when I am doing 90-degree, this is my XY plane. and my molecule was like this in this plane, right? This is my molecule. When I am doing 90-degree rotation, I will make it stand like this. Okay, so the molecule will turn up, suppose in a perpendicular plane, as someone said. Who told that? Pihu?
Yes.
Yeah, very good. So the molecule will go in a perpendicular plane. Now can you tell the numbers? Where shall I place 1, 2, 3, 4? What should
It
be
will
written
be
here?
the same. 1,
Yes.
2,
Yeah. 3 and 4.
3, 4.
Okay. Now this bond, which was XA, which was facing up, after the rotation, where will it go? Where will it go?
It will point towards us.
Yes, so it will point towards us. So let me write it like this. Wedges, it will point towards you. So it will come directly from like the screen. It will point directly out from the screen, and the other one will be inside the screen. And the molecule will be, suppose whatever your screen, mobile phone screen or laptop screen, in that plane the molecule is there. So this is like, so when you open the laptop, suppose you have a laptop, and when it's in the closed configuration, when your laptop is closed, the lid is closed, that is this configuration. Okay, and when you open the lid, what you do, you turn the lid up like this. Okay, this is your laptop in the closed state, and when you open it up, what happens, you will have two planes, right, like this. So now this refers to this opening up the laptop lid, is laptop screen, is a 90-degree C4, 90-degree rotation, right? So this is it. Okay, so the answer should be, okay, we have one more. So the molecule doesn't have C4, right? So this can be also the answer. It's a multiple choice question. And the last is the mirror planes. So this molecule, does it have mirror plane?
No.
Okay, so let me put the planes first. Let me draw 3 of them. Okay, now I'll put in one plane like this. Okay, one plane like this, and one plane like this. Okay, now if this is my Cartesian axis, so what is the name of this plane, the first one, according to the axis?
YZ.
So this is YZ. Second one,
X.
XY.
XY, and this one,
ZX.
okay. So we have these three planes. Now after applying these symmetry planes, what will be the orientations? Now suppose this is 1, this is 2, then 10.
It will go towards the left.
Yes, so this is 1, this will be 2. And what will happen to the up and down orientation of the X atoms?
It will be same.
It will be same. So this is reflection only, no rotation. So if there is no rotation along the, and also this is, the bonds are along Z and we are performing an operation along the Z direction, so there is no change. Now in this case what will happen?
XA will go down and XB will come up.
Like this.
Yes.
So here this was a perpendicular operation, so the orientation got changed.
Position will be changed.
No, position will not be changed because there is no rotation, it's only reflection by 180 degree. So I am not flipping over the molecule, you understand? I am not doing from here to here and I am not doing this. At the same place I am just turning the, I am just reflecting.
For the third one,
For the second one.
but I'm telling for the third.
Oh, okay. So for the third one, what should be the, where shall I place the numbers?
XA and XB will interchange position and orientation will be same.
Yes, so XA, XB. So in all these cases, the configuration of the molecule got changed. So what do we say? That it doesn't has mirror plane. So the answer should be, which is not present, should be inversion, C4 axis and mirror plane, A, C and D. Okay. Okay, the charge for my pen is gone. It's not writing anymore. So let's
Okay.
discuss fast. I hope you guys have completed all of this. For H2O2 molecule, both in the cis and the transplanar conformation, it's writing. Sorry. Okay, uh, can we just verbally discuss? So
Yeah.
I can show you the H2O2 molecule in here. So this website has a lot of molecules, for example. I don't know, H2O2 is, it will not be in here. This is okay. So you know what, how, yes, it's there. Okay, so this is H2O2 in, okay, this is not in plane. So the question asks the H2O2 molecule in plane. Okay, so this is a book kind of configuration, but the question asks the planar configuration. So both the OH bond will be in plane. Now consider that, and then then you deduce yourself whether in the cis configuration, so both the OH bond will be on one side, and in the trans configuration both will be 180-degree angled. So whether it has C2 present, can you draw this?
Yes, both have C2.
Where does the C2 pass through?
So in the trans one,
Hmm?
the um, the C2 will be perpendicular to the molecular plane,
Okay, yes.
and in the cis one, it will lie in the molecular plane between perpendicular to the OO bond.
uh, yes, yes, okay, that's correct. And both of them have sigma H. Sigma H is for molecular plane. Mukul, are you able to follow?
Yes, ma'am. I am
Okay,
also getting that.
okay, so sigma H is there or not?
Perpendicular to the axis,
Okay, yes. And sigma V?
not
Yes, sigma V will not be there. So whatever plane is, that one molecular plane is there.
sigma h.
Yes, sigma H is there, that's all. There is no other plane. And S2? S2 is C2 followed by perpendicular sigma.
Is it not S4?
What?
C2
S4?
followed by sigma.
Not always. S4 will be C4 followed by perpendicular sigma.
Sorry, but I read it somewhere.
Yeah?
Sorry, but I read it somewhere.
Okay. No, but S2, it will not be true for every time.
Okay.
It depends on the order of the molecule actually.
Okay.
S2 and S4. Okay, so for this one it has S2, S4, this molecule. These two like cis and trans.
C2 perpendicular to sigma.
When you do that operation on your notebook, or then check whether you are getting the same configuration what you started with.
The trans one has S4.
S4.
Yeah.
Okay. That's right. Now trans will be like this, and everything is in a plane. Okay, now I do, this is A, this is B, this is 1, this is 2. S4 means, sorry, it's gone again. Now you do sigma for this, any sigma. C4 plus perpendicular sigma, or any sigma plus perpendicular C4. You do any of this. So which one would you like to do first?
Sigma.
Okay, sigma. So let's perform this molecular plane sigma, this sigma H. So nothing will change, right?
Yeah.
Because it's the molecular plane, so the atoms doesn't change their place. Now the perpendicular C4, so this will be C4. So you do this, then what will happen? It will go like this, right? Piu?
Yeah, I was actually saying if we perform sigma
Hmm.
perpendicular to the plane, molecular plane,
Hmm.
and then C4.
Okay. This is my sigma H molecular plane, and the molecule is like this. This is 1, this is 2. And you are telling we have to perform a sigma like this. Correct?
Yes.
So what will be the orientation now? So this will be the orientation,
Yeah.
and the molecular plane stays where it was, sigma H. Now you have to perform perpendicular. So perpendicular will be along this direction or along this direction. So anyhow you will get
That direction.
so you'll get it back, right?
Yes.
So it has an S4 then.
Yes.
So okay, the question asked S2. Can you guys quickly check about S2?
It doesn't have S2.
Okay. So the here answer should be
The first one.
okay. We have to check the same thing for uh, this is trans configuration. Check the same for the cis configuration.
It does not have S.
So
Only P2 is common in both of them.
yeah, so the answer should be the first one only. So the next one, matrix multiplication. Can you guys do it? Everyone knows matrix multiplication, right?
Yeah.
So how do we perform? What is the first condition for two matrix to get multiplied?
The column of the first should match with the row of the second.
Yes. So if we have two matrix n cross m, and if we have the other matrix of the order p cross q, this multiplication is only possible if m and p are equal, right? Column of the first and row of the second should be equal. So here you have 2 cross 2 and here you have 2 cross 1. So this 2 is same, so we can perform the matrix multiplication, and the product should be a 2 cross 1 matrix, 2 row 1 column. Now how do you perform?
First row multiplying with first column.
Yes. So 3 into 4 plus corresponding elements will get multiplied and it will get added. Then
5 into 4 plus 8 into 6.
5 into 4 plus 8 into 6. So what will be the answer?
C.
So the answer is C. Okay, next one. The combination which has group and its subgroup. So do you know groups and subgroups?
In mathematics, I know.
Yes, it's same in math as in maths. It's same, but here you have to talk in terms of the point groups. Okay, so I think this question we can discuss next week when I'll tell you about group and subgroup.
Okay.
Okay, so next is the property that is not necessarily required for a group.
Commutativity.
Yes, so commutativity. Now what are the properties required for group?
Closure, associative, inverse, identity.
Yeah, as in maths, mathematical group, you have learned the group theory in maths set. This is a chapter in maths. So in group theory, what what properties form a group? A set of elements is said to form a group when they are when they satisfy
The
closure property,
associative,
associativity,
existence of identity element,
existence of identity element,
existence of inverse element.
and existence of inverse. Now, do you get the answer? Why do we need an identity element?
Oh, it's related to mathematics. Yeah.
Yes. So, if the E element is not there, it will not form a group. So, we need to have this element to follow the properties of a mathematical group.
Okay.
Now, what is closure?
If we made an operation with two elements from a set, that will also get pointed to the same set. We have taken the element from these two.
Suppose these are some elements in the set and the operation is a binary operation. Anything, the asterisk means not multiplication, it can be multiplication, division, subtraction, any operation or any group of symmetry operations, anything. Okay, so if we perform any operation on two elements of a group, the it should be present in the group. Okay, the resultant element should be present in the group itself. Okay, suppose I have taken the set of natural numbers and my operation is addition, right? This is my group. So a group is supposed to have two things: the set of entries or set of numbers or some identical things and an operation to be operated on them. So natural numbers, from where does natural number start from? What is
One,
natural number? Yeah, 1, 2, 3 and so on, and addition is plus. Okay, so if I do 2 plus 3, what I get is 5. So is 5 an element of natural number?
yes,
Yes.
Yes. So this is called the closure property. Close means the resultant element is enclosed within the group itself. We don't get anything new when we perform this operation. Okay, but if I take, instead of addition, if I take subtraction, okay, then I do 2 minus 3, what do I get?
-1.
Minus 1. Does minus 1 exist in the set of natural number?
No.
So it is not present in natural number. Now this set of natural numbers forms a group with operation of addition, but it doesn't form a group with subtraction operation. Okay, this is a group, but n and minus operation, it is not a group. You get my point? Because it doesn't follow the first property, first rule of being a group. First rule is it should be enclosure, the resultant element should exist within the group. So this
But
is the
it
meaning of closure.
first party only.
So what was the next one? Associativity. What does it mean, Mukul?
A star B star C in bracket equals to A star B in bracket star C.
What does it mean? Can you explain?
I'm not getting you. Sorry.
So what does it mean is the order of operation does not change the result.
Yes.
Right? If I perform the binary operation a asterisk b and then whatever result I get, with that I perform c. Okay, suppose a asterisk b is equals to x, then a asterisk b asterisk c will be what? X asterisk c. Suppose it gives me a number 10. Okay, for example, then if I do this operation, it will give me some number, suppose y, then the result for a asterisk y should also be equal to 10. Okay, the order in which I perform this does not change my answer. Okay, so this is why I told you, whether you perform rotation first and reflection after that or vice versa, your answer will not change because it is associative. It forms a group and hence it will follow the associative property. Okay.
Okay.
Okay, the next one is, third property is existence of identity, which is E in our case. In like in case of molecules, the existence of identity, the identity element is E, right? And suppose the set of natural number and addition, in this case, if this was my group, the identity element was,
0.
yes, here it is 0, because you add anything to this 0, you get that element itself. So similarly, you perform on in E on any molecule, you get the molecule itself. So this is the identity. And the fourth and the last one is existence of inverse. Okay, so according to this, existence of inverse means you perform the operation. Suppose you have an element A and it should have some inverse. When you operate it with that element, you should get the identity element back, 0, right? But you see here, in case of natural numbers, suppose I have 3, is there any number in the set of natural numbers which I should add to 3 so that I get 0?
No.
No. The actual answer should be minus 3 here. I should add minus 3 to 3 to get 0. But this minus 3 does not belong to the set of natural numbers. Right? So I cannot take minus 3. Hence this group, this natural number with plus operation does not form a group. It passed all three properties. It passed the closure property, it passed the associative property, it passed the identity property, but it doesn't contain the inverse elements. Hence, it doesn't form a group. So instead of natural number, if I take the set of integers, then it will form a group. Integers and plus or minus. Then it will form a group. Then it will have all four properties satisfied. Okay?
Okay.
Pihu understood?
Yes.
Okay. Okay, so this is all for today. uh, so we'll discuss week 1 assignment next week, okay, and the following weeks like that, okay.
Okay.
So I'll close it for today now.
Okay. Thank you.
Yeah, thank you for joining, everyone.
Thank you. Can we get the PDF?
Yes, you will get the PDF. I will just upload it in few minutes. And you will get the PDF and as well as this recording of the lecture. Okay, so I'm closing the session. Thank you.
Okay, thank you.